Okay, so welcome to the second lecture on magnetic fields, magnetic effects of current, electric currents. So today what we will do is, before diving into the magnetic effects of electric currents, we will revise a little, okay? And also we'll be writing some definitions so that it's easier for you to understand the concepts. Now let's look at the definitions of magnetic field. So when we are talking about a magnetic field, it's basically asking a question if a force acts on that point or not. Okay, so if a force acts on a magnetic pole, in practice a pair of poles, there is said to be a magnetic field around that point. So for example, if you have a magnet here, okay, so if you have a magnet here, and let's say this is north and south, and because we also have already learned how to draw magnetic field lines, so maybe the field lines is like this. Okay, maybe the field lines is like this. So in practice, the field lines are not visible with the naked eyes, but there are some tools with which you can visualize the magnetic fields. But how do we define a magnetic field? So when we define a magnetic field, what we are basically saying is, if we put a magnetic pole on the point, on any point, let's say we put a magnetic point pole on this particular point here, okay, we know that the magnetic compass at this point will be affected. Okay, there will be force acting on this magnetic needle. So if there is a force acting on the magnetic needle, then we say that this needle is in the vicinity of the magnetic field. Okay, so it is in the magnetic field. So this is the way how we define the magnetic field. Now, let me just recall a little bit about what we also said last time, that firstly, first point is basically the direction of the field lines. In this case, the magnetic field lines is from north to south. Okay, so direction of magnetic field lines is from north to south. Secondly, the field lines never intersects. The field lines never intersects. Okay, because if it does, then there will be some ambiguity. Let us just look at one example. If we say the field lines cross, like for example, if the field lines that I've drawn is like this, let me just do it in another color so that it's easier to visualize here. So let me say that this is the new field. This is the field lines that assumed to be true. Okay. Now you can see that the brown line and the black line here both represents a field, but they're intersecting each other. Now, why is this not possible? Let's look at it. And the reasoning is pretty straightforward here. Now, if we put a magnetic compass on any of the points on the field lines, it seems valid, except at a point where they intersect. For example, if I put a magnetic needle here, I know that my north will be pointing like this. If I put a magnetic needle here, will be pointing here. But what if I put my magnetic needle at this point where it intersects? Would the brown line be more effective, or would the black line be more effective? So there's an ambiguity at this point. So because the magnetic needle cannot both point at the same time in the two different directions, that's why we say that the field lines never intersect. Okay, because if they do, then we see that there is some ambiguity in the directions of the field at that particular point of intersections. So that's why the field lines never intersect each other. Okay, and the third point is basically the fact that the strength of the magnetic field is represented by the density of the lines, density of the field lines, Okay, so these three points are pretty straightforward and very important for you all to remember. Now let's now finally talk about the magnetic effects of electric current, and that's the important part in this chapter. Okay, so let's look at the magnetic field due to a current in a conductor. Okay, let us assume there's a wire in which a current is flowing through it. Okay, so there's a current I flowing through the wire. Okay, so now when people first conducted an experiment where the current was flowing through a current, they found out that the wire carrying a current had a property that was very similar to magnetic properties. Or in fact, we could also say that the wire carrying current behave like a magnet. So that's the observations that we can make when a current is flowing through the wire. So the first observation is basically the wire behaves as a magnet. How do we know that? Because when we put a magnetic needle here, so maybe the needle is somewhere here like this. If you put a magnetic needle, it deflects. Okay, there is some force experienced by this needle. So we can say that there is a magnetic field. And the second observation is basically that the magnetic field lines are circular. For example, if the current is flowing through from left to right, in this case, then we can draw a field lines which will look something like this. So it will look something like this. Maybe my diagram is not so good, but I can try to draw it almost like a circle. Okay, so something like this. Now, it's a circular field. It's almost like the wire is in the middle of the green circle. Okay, so the green lines here represents a magnetic field. Now, the third observation could also be made in respect to the direction of the field. Because it's a magnetic field, it should have a direction, right? So what is the direction of the field? So in order to understand the direction of the field, there is a rule that you can use. So it's called the screw rule. Okay. Screw. Or you can say the right hand screw. So the right hand screw. Now, if you curl your hand in a way that it looks like this, like a thumbs up, and your thumb is pointing towards the direction of the current, so the curl of my fingers the direction of the curl of my finger basically represents the direction of the magnetic field. So in this case, the direction of the magnetic field is something like this. So it goes from clockwise. Okay, so it's clockwise direction here for the magnetic field. Let me repeat it again. The right hand screw rule basically says that if your thumb represents the direction of the current, my finger, the direction of the curl of my finger represents the direction of the magnetic field. Okay, so now let's move on to the next section. Okay, so let me just rewrite the observations that, restate the observations that I have just stated. Okay, so when we talk about the magnetic field pattern here, firstly, it's circular. Okay, secondly, is that when you go away from the wire, the magnetic field strength decreases, which means that the magnetic needle experiences less force when it's away from the wire. Okay, so how does it behave exactly? We have not studied that, but that's the observation that you have to remember. Okay. Now the other thing is, how do I represent this sort of magnetic field lines in a much simpler manner? How do I represent it in a 2D figure? So that's the next task that we will be doing, and so this 2D figure basically simplifies our diagram. If you want to represent the field lines of a wire carrying conductor, current carrying conductor, what you basically have to do is imagine an arrow. Okay, so if you imagine an arrow, let's say the arrow is going away from you. So it means that you see the tail of the arrow. So the tail of arrow is simply, it looks like a cross, right? So think of the tail of the arrow as being this one. So the tail of the arrow basically represents the current flowing away from you. So it's going towards the page. Okay. So if that is the case, then according to our right-hand screw rule, if you point it towards the page, you will have to draw a circle that's around the arrow, which looks like this. So let me draw a proper circle here. Okay, so maybe this is the first fill line, and then the second fill lines could look something like this. Let me just make it a little bit more here, and then maybe the third one, last one. Yes. So if you want to represent a fill lines, then again, we just stated right now, you just point the thumb towards the page, because that's the back end of the arrow and it's going away from you, and the direction of the field is circular. So it's clockwise like this. Okay. So this is basically a 2D representation of a magnetic field of a current carrying wire. Likewise, if the arrow is coming towards you, you only see the point, right? So you only see the point of an arrow. So if it is like this, then again, your thumb is pointing away from the paper. So it's going perpendicular, it's away from the paper. So if it's going away from the paper, the finger is curling this side, right? So it's curling in the anti-clockwise. So the field will also be in the anti-clockwise direction like that. Okay, so this is maybe this is the first field lines, and maybe this is the second one. Let me just draw 3 field lines here. Like this. So this could be the third field lines here. So the direction is exactly the opposite, like this. anti-clockwise. Okay, so basically cross represents current flowing into the page. So current flowing into the page, into the page, into the page, excuse me. And the dot represents the current flowing out of the page. So these are just some representations of a fill lines in 2Ds. Okay. So now let's move on to the next part. Let us look at one of the questions that's related to the magnetic field of a current carrying wires. So in this case, we have 4 different wires here. So 2 wires here. So the 2 wires in which the current is flowing into the page, and the other 2 wires here flowing out of the page. Okay, so the question is basically asking us to find the magnetic field at a point P, or more appropriately, we could say finding the effective magnetic field at point P. Okay, now let us look at each of the, let us look at this question by doing it individually. Okay, so first let's look at the wire that's here. So first let's look at the wire, that's this one. So like I said, for any current carrying wire, the field is always circular. So let me draw a circular field. Okay, so I will draw a circular field. Let me change the color here. Let's say a blue one here. So let's say I have a field here. Now I'm only interested in point P, so I'll draw a big enough circle so that it fits the point P. So like this, something like this. Yeah, perfect. And we also said that if a current carrying wire is, I mean, if the current is flowing towards the page, that means you have to point the thumb towards the page, and the curl of your finger is basically giving you the direction of the magnetic field. So in this case, the direction is simply this way, this direction here. But at point P, like you know that it's this direction, right? So that's the direction of the magnetic field at point P. Okay, so let me just erase this one, and let me just shift this one a little bit and just make the direction for the point P. So the direction of the magnetic field at point P is basically this. So this one, due to A. So let me just say this is A. So it's due to A. It's color coded, so I think it's okay if you don't believe it. Now let's move the magnetic field to the second one. So if we have a second one here, let's say like this. I mean, this is okay. Okay, so this is fine. Again, the magnetic field is still the same, right? The only difference is, what I mean is it's still clockwise, but direction is different in this case. So due to B, the magnetic field is here, right? Because the direction is like this, it's clockwise. So magnetic field's direction is this. So that's due to B. Let me erase the this one. What about C and D? Let me just move this a little bit up so that I could fit everything down here. So maybe we'll do it like this. Now, if I move to the C part here, now you know that the current is in the opposite. The current is flowing outside, right? The outside. So it has, the thumb has to point towards you. So if the thumb is pointing towards you, you know the curl of the finger is in anti-clockwise. So the direction of the field is basically this. So it's anti-clockwise, so it's like this. But at point P, I know that it's parallel to, let me just to distinguish these two, I'll draw two separate lines. So it's parallel to the green one. Okay. And also, similarly, if we do it for the last one here, if you look at the field's direction for the, let's say this is C, and for the part D here. So let's say this is D. So for the D part, also you see that the field is parallel to the brown line. Okay, because the field is anti-clockwise. So now you have 4 vectors here. So magnetic field is a vector, right? So the effective field is towards that direction here. So, excuse me. So the effective field will be towards that direction, right? Because both the fields are pointing in a way that the resultant will be towards the direction of the red field. So this will be the resultant magnetic field. So now we can erase the magnetic field here and just give this as the direction of the magnetic field for this at this point P. Okay, so this will be the resultant magnetic field. Okay, so we will do that much for today. So next time when we meet, we will talk about the forces acting between two current carrying wires. Bye-bye, take care.